Welcome and shalom to this to the Australia-Israel Scholar Seminar Series. I'd like to start by acknowledging the Turrbal and Yagara people as the traditional owners and their custodianship on the land on which we meet today in Brisbane, Australia, and I pay my respects to their ancestors and their descendants, and I extend my respect to people joining us from all Indigenous lands in Australia and elsewhere. So I'm thrilled to welcome Professor Avi Zadok from Bar-Ilan University. Avi did his PhD at Tel Aviv University in electrical engineering. He was a postdoc at Caltech in the US and joined the Faculty of Engineering and the Institute for Nanotechnology at Bar-Ilan University in 2009. And I just heard from Avi that soon his whole lab will be moving to Technion, Israel's Institute of Technology. So today, Avi will be talking about silicon photonic circuits. So please, everyone, welcome Avi, and I'll get you to take it away. Thanks, Avi.
Okay, thank you very much, Joe and Yoni for organizing the series. Can you see my presentation?
Yes, looks great.
Okay.
Just into presentation mode. Yeah.
Okay, can you see it now?
Perfect. Thanks.
Okay, so I'm delighted at this opportunity to speak here, and I appreciate your support of us, of Israeli academia, and of Israel as a whole in these trying times. And in the next 15 minutes, I want to tell you a little bit about the field that I'm working on. It's called Photonic Integrated Circuits in Silicon. I'll try to explain more or less what this is, and I will not emphasize so much our own results, or only briefly, in favor of giving you some sort of flavor of what this field is about. And the motivation for these works is communication, is how we communicate vast amounts of data. The data needs to be carried somehow, and we carry them over electromagnetic waves in various forms, in various frequencies. And over the last 40 years or so, the almost exclusive manner to communicate and relay huge amounts of data is over light, sending light waves within optical fibers, such as these yellow things that you see in this image. And this is how we send data far away. And this field has been extremely successful over the last 3-4 decades, to such an extent that if you could somehow take out all the fibers that are installed on the face of the earth and underneath the oceans and connect them in one long line, you will reach planet Uranus and back. There's that much fibers installed. So optical communication, in essence, is what makes internet possible, because this is the only way we have to share so much information over such huge distances. And the key has been really distances, because we have set up optical communication to connect between faraway locations. Only that now, that range consideration is drastically changing. Nowadays, connectivity on a vast scale isn't just between cities and countries. It happens within offices, within racks, within computers, within boards, which means that the number of such systems that we require to share data over optics is way, way larger. It's no longer the case like we had a small number of systems reaching very far. Now we have vast numbers of systems that have to reach very close distances. And this changes the landscape entirely. All of a sudden, we care about volume. These systems need to be small. We care about mass production. We need many. We care about cost, because when we make millions and millions, every penny matters. So this calls for integration. It calls for building our systems, not in boxes and modules and cumbersome racks of equipment, but on chip. This is actually the way electronics works for 70 years now. And we are pushed to do the same for the sake of optics. And this isn't just data. Additional applications of Photonic circuits includes lasers, rangefinders, what we call LiDARs, for autonomous navigation, various sensors, quantum technologies, signal processing. All of these applications leverage and benefit from the integration of photonics to the circuit level. So if we've been accustomed to chips, quote unquote, being the realms of electronics, then they are no longer exclusive. We are more and more pushed to use such integration for the sake of light. And this industry is actually growing by 30% a year, and it is really already amounts to some $20 billion annually. So it's a pretty big deal. So let me try and illustrate basically how this works. The most fundamental building block or structure or function that we have on a chip like that is how you relay light from point A to point B. And we propagate light in structure that we call waveguides, such as the one you see here. A waveguide has a core region. In this demo here, it's a piece of silicon, again, the same silicon of electronics, and light can be guided in that silicon slab here without leaking away. For that to happen, this core region needs to be surrounded by other regions, which we call cladding, and these cladding regions should have an index, refractive index, lower than that of the core. In the most standard arrangement, these cladding regions could be glass, silicon oxide, or could be air, above and to the sides in this demo. And since the index in these domains is lower than in the silicon itself, light can be guided in the silicon. What you see here is a calculation which shows how the electromagnetic intensity is spread out inside the waveguide like that. What you can see here in these black lines are the boundaries of a silicon layer with glass below and with air above. And the silicon layer is patterned to form this narrow ridge that you see here, which is a little bit thicker than these domains to the sides. Because of this extended thickness of silicon, light can be confined to this central domain and be guided within that central domain without being dissipated and lost away. And then we can pattern a cross-section like that along the surface of a chip and carry and guide the light where we need it to reach, from point A to B and C, and so on and so forth. So this is the most fundamental building block that we have. A part of our work is to solve the equations of electromagnetism, solve the equations of optics within these structures, and predict just exactly how these modes or solutions will behave, how they are spread laterally, how they propagate, how they accumulate phase, how they accumulate loss. All these are worries that we have to deal with as part of our design phase. So if the most basic building block is a single waveguide, the next level of, say, construction will be placing two of these waveguides next to each other. When we do that, we end up with what we call a directional coupler, like you see here. You see two of these incoming waveguides, and they're drawn close together, and then they are separated further away. And in this domain of closer separation, light can actually be switched from one waveguide to the other. It can be split, or in our lingo, we would speak of coupling of light from one to the other. So if we have launched a signal just from one of these ends here, and we observe the output, we may find that it is partially divided between these two outputs, because these two structures have some opportunity to exchange signals and for mutual effects within this region in which they are more closely separated. So this is how we can split and combine and divide signals along our circuits between one route and another. What could you do next? So if we're going from one waveguide to two waveguides being a coupler, we can then proceed from one coupler to two couplers in series and construct something that is even a little bit more complicated and rich. So here is one coupler like I've shown you, and here is another. And the two outputs of coupler number one are now connected to the two inputs of coupler number two. So these two together, with the delays between them, these arms connecting them, become one black box with a pair of inputs and a pair of outputs. And it could be instructive to follow how signals would propagate along a structure like this. So if we follow, say, the uppermost input, the upper port, and try and track back how it might reach, say, the upper output, we identify two possible paths, or two possible routes that light might take. One possibility is to cross coupler number 1 in the upper part, and then cross coupler number 2 again in the upper part and remain in the upper branch. But there is another option in which light can be partially crossed to the lower arm here and then cross back to the upper one. So when we observe the output, we actually observe two copies of this input port here combining together following different paths. Now, if we deliberately make one path shorter and the other one longer, then in essence, we combine replicas that are delayed, one with respect to the other. And a construction such as this works as a filter. If we monitor just how much power is reaching the output here, this power is a function of optical frequency omega, because these two arms might represent interference of the replicas that is perhaps constructive, or perhaps destructive, or perhaps otherwise. And if we go ahead and calculate and draw this, you can see output port number 1, that's in the blue, output port number 2, that's in this orange here, and the two are complementary. Some certain wavelengths or frequencies of light emerge at the first output, whereas others emerge at the other, and some are somehow split. So the response is a function of frequency. And a response which is frequency dependent makes for a filter. So this is a first rudimentary device that can filter certain frequencies and reject others. Only that this particular filter is quite restricted, because if you can follow here, the selectivity isn't that great, transmission isn't uniform, so perhaps we would wish for something better. And we can do that if we cascade a number of these devices one after the other. So I'm walking you through a certain level of integration here from one waveguide to a coupler, from one coupler to an interferometer, and now from one interferometer, one unit cell to many, and here we have relayed 16 of them. So now the input is split between no less than 16 outputs, and if we construct this carefully enough, we may end up with a separation of frequencies, each one taking its own port. This is the actual chip, by the way. This is a design made by my own team and fabricated in Israel in the semiconductor foundry of Tower Semiconductors. That's in the north of the country. So this is how a chip looks like. If this is a schematic layout, this is how it appears in reality, and you can see the input and the 16 outputs and the various stages in between. And if we play our design just right, we end up with the response that you see here. And this is more or less where I'll stop for questions in a couple of minutes. What you see here is 16 measurements of the transmission between the common input and all 16 outputs, each in a different color. And what is signified here is that each of these physical outputs obtains just a specific range of optical frequencies or wavelength. That wavelength appears in output 1, and that wavelengths appear in output 2, and so on and so forth. Now, this is serving us to divide or route or multiplex channels of data. Within each of these wavelength windows, we can accommodate a large amount of data, tens of gigabits per second, hundreds, maybe even terabits per second of information, and we can send it where it is needed. Whereas another bunch of data, also possibly terabits per second wide, will be directed someplace else where it is needed by another user. So this function or capability to multiplex and route and separate and combine data streams is among the foremost application of these silicon photonic circuits. I will now skip some other things and take you to my concluding statement here, or I should say take-home message regarding what, in my view, is a good objective or a not so good objective for the silicon integration technology. in the photonics point of view. So the relative strength of photonic circuits, such as the simple ones I've shown, is their capability of handling huge amounts of information. This is why we're using them for communication of data in the first place. This is what optics is great in doing, in carrying and dealing with fantastic amounts of information. That's the upside. Of course, every technology has its drawbacks, and silicon photonics is no exception. And the drawbacks for this one is the size of the elements. If you recall the picture of the chip that I showed you, it contains a rather modest number of elements over a size that is many hundreds of microns by hundreds of microns. If you compare that with electronics, the dimensions of an electronic element, a transistor, measures in the tens of nanometers, maybe even single-digit nanometers. So there is a huge disparity in size between optical building blocks, which are huge, and electronic counterparts, which are tiny. Now, this is limiting us in the number of elements that we can accommodate. The integrations in the billions and billions of elements that electronics is accustomed to is really far away from our perspective. And we have to choose the objectives, the goals, the purposes of our circuits accordingly. So a good objective, in my opinion at least, would be a task that can deal with vast amounts of data, such as the routing of these terabits per second channels that I've shown you. This is good for optics. And at the same time, the tasks have to be comparatively simple in terms of complexity. It should be a task that can be broken down into a modest number of elements because we can only accommodate a modest number of elements. And this is keeping us somehow simple in what we can do at the moment. But since the limitations of element size is a rather fundamental one, I believe that these guidelines will remain with us at least for an appreciable amount of time. Let me conclude here by acknowledging my team. Here are a couple of group photos taken some years back because these are the guys who do all the hard work while I'll do the talking. So I'll stop the sharing here, and thank you all very much for your time and support and patience. And if you have any questions, I'll be glad to take them.
Thank you so much, Avi. That was really great. I love the combination of high-level, big picture stuff with some examples of what you're doing. I'd like to open up the call to any questions from the audience. You can either type in your, yes, we already have some questions. Thank you, Neri and Ron. So Neri says, what is the reason for photonic circuits being so disproportionately large? Is it just insulation? Okay, so it's a great question, and one that is been on our mind as a community for a while. The problem begins with the wavelength. We are using light that has a wavelength in air of 1.5 microns. If you consider the refractive index of silicon, that wavelength becomes shorter somewhat. It's say 500 nanometers. And it is quite difficult to confine light to volumes or dimensions that are deeply sub-wavelength. So if we are stuck with that wavelength of light, we can push it and confine it into hundreds of nanometers dimensions. But it's really difficult to go below that. So if you think of a cross-section of a waveguide such as I've shown you, in terms of width, in terms of height, it is somehow stuck to the hundreds of nanometers dimensions. And these are the optimistic ones. The really painful dimension is the length. Our problems begin with accumulating delays, for instance. Suppose you want to, if you make a filter such as the one I've shown you, you have to delay your signal and then combine it back. And these delays, because the speed of light is so fast, they cover distance. So thus far, we haven't found a really elegant way around it. There are attempts, there are details,
Some devices can be made smaller, others not so much. Again, time is too limited to dive into ultra specific stuff, but the difficulty is a rather fundamental one. It begins with wavelength.
Fascinating. We're getting quite a few questions. Neri says, thank you for answering that question. And we have a question from Ron, who was wondering if there is an ideal multiplexing number, or can you ideally continue creating better and better circuits? Is there a number where the noise gets too close to that of the signal?
Okay, so again, the great question and a highly relevant one. It is possible to multiplex tens of channels practically. In like very high-end systems, we can perhaps think of 100. It's kind of hard to go beyond that because, again, of the element count. Very broadly speaking, to separate n channels, you will need the order of n elements to do that. Maybe a bit more, maybe a bit less, but the number of elements scales with the number of channels you're dealing with. And as they become more closely spaced with each other, they also require to accumulate longer delays, which make them larger. So we are able to accommodate tens of these elements, maybe in the few hundreds, which again would correspond to, say, tens of channels, but that's where we are today.
Great. We have a question from Eden who says, how do you keep track of each of the wavelengths, or is there some mathematical formula to determine which output will carry which frequency?
Okay, so again, thank you for this question. This is really has to be built into the circuit layout because these frequencies add up in a constructive or a destructive manner depending on how exactly these paths of light are defined, and they need to be defined to a very high precision. Again, it's a wavelength thing because if the wavelength is half a micron, and suppose I've gotten one of these paths wrong by even half of that, 250 nanometers, that alone can switch me from a constructive to a destructive interference and take a channel from what it's supposed to be to someplace else entirely. So the design and fabrication of these circuits must define each of these lines you've seen in the picture to the level of tens of nanometers in length. And if you do that, and then the splitting and routing of channels is built into that hardware. Yeah, so I hope that answers.
That sounds great. Eden also asks for any books or papers you'd recommend for further reading on this topic. Perhaps if you share them with me by email, I'll put them into the recording YouTube description.
Okay, there's a few things I can offer. There's a great book by Graham Reed, a professor from UK. It's called Silicon Photonics, and I think it's a very good one. And I used it in my teaching. And I also there are my own notes that I use in class, which I will be glad to share with everyone who's interested.
Oh, wonderful. So Eden, maybe if you send Avi an email, it's located on his website that we've linked to from this event, and I'll post it in a minute too. And we have a final question from Yoni Nazarathi, who asks, how much is the field influenced by manufacturing of traditional electronic silicon? That is, if wafer fabs were reinvented solely for photonic purposes, would your research differ a bit or a lot?
It will be different. It will be way different because to us, since we have been late to join the party, silicon is reality. And if we want to stand any chance of implementing our structures and ideas on a large scale, we have to coexist with electronics, we have to co-integrate with electronics, and we have to live according to the rules of electronics. So our design space, to a large extent, is defined or restricted by what is possible in electronics fabs and what is not. And everything that is not possible, it's not like pushed away from the table entirely, but it requires a much larger amount of effort to get by. So we would go way out of our way, if I can use that phrase, to accommodate ourselves to the directives of silicon electronics. Yeah, it's a big deal.
Well, that's really great. Are there any further questions from the audience? You are welcome to unmute if you would like to ask your question in person. Otherwise, I think we'll wrap it up for today. I'd like to thank Avi for his time in presenting today. It has been a really fascinating insight into silicon voltaic photonic cells and power. And I thank all of our participants. I hope you can join us at some future seminars, and this recording will go online soon, so you can keep track of that on our YouTube channel.